Hey, Katie.
Hi, Ben.
Have you ever stolen anything?
Well, that just go right in for it, don't you?
I did. Because I've stolen something, and I'll tell you about it after we start the podcast.
Okay.
All right. You're listening to Linear Digressions. So I was in Safeway once, and you know those bulk bins? I stole one Andes Mint. And
Ben.
then after I left the store, I felt really guilty about it. That's all.
Okay.
Sorry. So we're talking about theft of something, Katie.
We're talking about theft of machine learning models today,
How I didn't know
which
you
are
could
a
steal
little less
those.
tasty than Andy's mints. I know, right? But this is, it's funny. I was reading this paper, and as soon as I read the abstract of the paper, I was like, oh, of course you could do this, right?
Interesting. Okay. So I guess when I think about machine learning algorithms, I think about them typically as things that are already known because so many of them are open sourced, right? But it does stand to reason that there could be a model created by a company or by somebody who wants to maintain a strategic advantage, and that they wouldn't want that model to get out there because then someone else would be able to use that model and they wouldn't have their advantage anymore.
Yeah, I think that's a really good summary of what could be going on here. So the paper that I am referring to is called Stealing Machine Learning Models via Prediction APIs. And this was just put out in the last month or so. Um, and yeah, so the idea here is let's imagine that you have some kind of machine learning as a service business. And so let's imagine that you, Ben, are the person who runs that business.
Got it. So
And
I've
so
created this super awesome model
yeah,
and I'm exposing some kind of endpoint so somebody else, so all these other programs can hit my endpoint on my server with some query, and then I'll run my model on it and I'll send them back the result.
yeah. So let's imagine that it's a simple linear model, and it's a linear model that predicts, I don't know, what do you want to have it predict?
Let's say income. So I guess you give me a bunch of information and then I run this information through my model and predict the person whose data this is income.
Okay, sure. So let's say that the thing that you had to do to build this model was you went out and you ran a very expensive survey where you actually went to people's houses. Maybe you got them to agree to some kind of like reporting automatically from their bank account, even. You
Yeah,
gathered this very labor intensive data set.
I can't be very persuasive.
Sure, yeah. Let's say you just paid them.
Okay.
But you've gone out, you've collected this data set, so you have this very rich idea of all these people, their, let's say, their demographic attributes and their incomes. And so
Right.
from this, you're building a model that says, here's the coefficient that we associate with age. So that's how much your income tends to change with your age. Here's the coefficient that's associated with your gender, with your industry, with how much education you have, whatever.
Yeah, and now let's imagine that this model is very, very successful. It's a very good model. It's better than maybe any model out there for predicting this stuff. And rather than making an open source project, I decide, you know what, I'm going to monetize this. So I create that service and I allow people to submit information and I run it through my model. I send them back a result and maybe I charge them like, I don't know, 1 cent for every time they run it through the model.
Yeah, bingo. So then what I can do as an adversary, there are several different things that I could potentially steal here. The easiest one to steal is the actual model itself. So what I can do is, let's imagine, this is an oversimplification, but let's imagine it's a one-dimensional linear model. So it's basically a line, y equals mx plus b, right?
Yeah.
So let's say that you return a prediction and potentially some uncertainty on the prediction about someone's income. So what I can do is I can say, let's say the particular linear relationship that we have is, let's say your income only depends on your age. And I don't
Right.
know the relationship between your income and your age, but I know that it's just those two variables. So then I might have somebody who's 30 years old and I say, what's their income?
Oh, that's $60,000.
Cool. And now I have someone who's 50 years old. What's their income?
$100,000.
Okay, so now I have 2 points. I have an age and an income for both of those points. And I've said by design that it's just a simple y equals mx plus b equation. I can now solve for the complete equation of that line. And I can interpolate now for every point along that line what their income is going to be, just based on those 2 data points. I've completely reconstructed your model. I've just stolen your model from you. So there's no reason why I would have to ask you anymore and pay a penny every time. I can just recreate I can recreate the model now. And so that's basically
that's a really, really simplistic example.
I mean, it is, but for a linear model, if you know, like all of the features that the model is built upon, basically the idea is if you have some idea of what the input space is, and then you just ask, it might be d-dimensional, but then if you make d+1 queries on it, you can reconstruct the entire thing. It's just like, it's like a linear algebra statement almost.
Right.
That, if it obeys those rules, you can reconstruct the entire model.
Yeah, that makes sense.
And,
and then in more complicated examples, you might need to pay more pennies to reconstruct this, and you might have more error. But basically what you're talking about is reverse engineering. You put a bunch of input in, you look at the output, and you say like, okay, how do I think this might be working under the hood, right? To transform these inputs into these outputs. And then once you get kind of a good guess of the way it's working, you validate it with a couple more pieces of input, and potentially you've stolen either the exact model or something very close.
There are different types of models that are easier or harder to steal. So one of the things that I assumed going into this is that I know that it's a linear model.
Right.
And I wouldn't necessarily know that. You could have something like a neural net or a decision tree. And each of those is going to have a different complexity in terms of how hard it's going to be for me to reconstruct it. For example, a decision tree is harder because it's nonlinear. It can be making like weird, very sharp cutoffs in a way where I would need to take more data to find those discontinuities. So they have different examples for each of these different algorithms. What they actually did to write this paper was they built models on some of these popular services and then tried to steal their own models and demonstrate that you can do it with, the various algorithms that are kind of
that's
suited.
So interesting.
Yeah. And one of the other things that I should say is that predicting income is kind of a continuous problem, but they also do it for classification as well. So many of these classification algorithms that will return to you a prediction and also an uncertainty on that prediction. So they might say like, oh, we think that this is a dog and we're very confident in that prediction, or we think that this is a house and we're not so confident. And especially if you have those confidence intervals, then that helps a lot too, in terms of like, if you're thinking of yourself as the adversary, you would like to have that extra piece of information about how confident the model is, because it makes it a lot easier for you to like basically tell where you need to take more data and where you already have things pretty well mapped out. And then the other thing that I thought was really crazy about this paper is in certain cases, this is harder, but in certain cases, remember I said you have this expensive data set that you went out and collected and you use that as the underlying data when you were training your model?
Right.
In certain cases, I can even reconstruct examples from your original training data based on queries of the model. And this I do not understand quite as much. I didn't have a chance to really dig into this part of the paper, but they were able to basically regenerate examples from their training data sometimes, not always. This is harder, but it is possible that even the data itself could be compromised.
Oh, that is really fascinating. That's crazy.
Yeah. So one last thing to slightly pivot before we sign off, which is a little bit of an addendum to our episode that we did last week about regularization, right? Mm-hmm. I usually try to do these at the beginnings of episodes, but then I forgot. So got a really good comment on Twitter, which is referring to the fact that I actually overlooked an important reason why you might even do regularization that we should talk about. So let me give, first of all, credit to Amir Ranama. I hope I said your name right.
Good said.
Yeah, who pointed this out. And
just really quick summary, what's regularization again?
Oh, right. So regularization is the idea that you have an aspect of your algorithm when you're actually training a machine learning algorithm, like a supervised classifier. You have a term that penalizes the complexity of the model that you're building and effectively ends up throwing out features if they don't seem to be adding a lot to the performance of the model.
Right. So that allows you to make your model run faster, be more performant, while not necessarily changing the results that you get all that much.
Yeah. So Amir kind of asked a question about, like, why didn't you say this as some of the important reasons why you might want to do this?
What was the thing he said?
So 2 things, overfitting and sparsity. So overfitting is just the idea that if you have a model that has a lot of complexity to it, it can become kind of overfit. It learns not just the general patterns in the data, but sometimes the little quirks and wiggles in the data, and that actually makes it not as good of a model. It'll tend to make mistakes on other cases because it's learned the training data in too detailed of a way.
Right. So your training data is supposed to be a sample of a larger data set, but because it's going to have a finite size, some kind of reasonable size, it's going to have those nooks and crannies that don't necessarily exist in the phenomenon that you're trying to study.
Yeah. So if your model gets very complex, sometimes it ends up fitting those nooks and crannies, which is not what you want it to do.
Yeah.
So controlling the complexity of the model helps control overfitting. And then the second thing that Amir mentioned was sparsity. So sparsity, that's when you have data where it tends to be, I kind of think of it as when you have data that's mostly zeros instead of ones. So classic example is maybe Amazon data is very, very sparse because for each person, they only buy, even if they buy tons of stuff, it's still only going to be a tiny fraction of all the stuff that's available on Amazon. And for each of the products, even if it's a very popular product, it's only going to be bought by a tiny fraction of the users. So that would be an example of where you have very sparse data. And so sometimes you can, especially when you have, kind of hashtag big data, it tends to very often be kind of sparse. So it can be really big, but there isn't a whole lot of information in there. And so overfitting can help you deal with that a little bit. You can still dump that really big data set into an algorithm, but if there's some regularization, then it can help you trim away some of that stuff that doesn't seem to have a whole lot of information in there, or at least information that's important for the thing that you're interested in. So I think that's what Amir meant by sparsity. Sparsity, sometimes people are thinking of different aspects of data when they say that, so that was a little bit my interpretation. But that is a very good point as well.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.